In case you're watching on YouTube and wondering what's going on, the situation is that we have a Zoom and we have a YouTube happening at the same time. And on YouTube, hopefully the sound is working. And we use a certain piece of software to connect the two, to bridge the two systems together. And so what's happening right now is it seems like right now something is not bridging. Let me go and see what's happening here. I'm going to go and check. So you'll see me vertical for a moment. I'm trying to figure out, oh, that's interesting. Okay, do we have connection now? Let's see. Oh. So it looks like I had given the wrong advice to the person who was helping us with our technology. The sound's back. Oh, good. Everything works. So yeah, I want to apologize. I'm Po-Shen Loh, and I had sent some new suggestions to improve our technology just a few minutes before the stream started. And apparently, as all things work, if it ain't broke, don't fix it. So it wasn't broken before, and I managed to break it. But regardless, welcome to our live stream. I am Po-Shen Loh. I am not exactly in the stream right now because, well, unfortunately, I'm on the road. This is the Pacific Ocean. I actually just spoke at a competition called Integrals out in San Diego, and I'm on my way back up to the airport because I am going to be out in England by tomorrow. However, if you're here for Math League, you're in for a treat because the problems are really interesting, and we're very happy to collaborate with Math League on a regular basis because, well, it's very nice to have a math contest that you can engage with every single month. And they do have this. If you aren't participating in the Math League contest yet, we strongly recommend that you do. Now, every month after their contests are done, we have a live solve. And the live solve is done by some of our incredible stars. We have high school students who are really good at math. They have a lot of math background, but they also are great at performing. And they'll actually be taking over from here. So with that, they also have a system called, not Rat Relay, called Chat Relay. They have a system called Chat Relay. And on that system, they'll explain to you how it works, but you'll be able to participate and your comments will all be on screen and it'll be awesome. With that, I'm going to pass it over to Audrey and Sam, who are going to introduce each other and run with the rest of the show.
Awesome. Thank you so much for that, Professor Lowe. Okay, let's get into a couple of introductions. Today I'm gonna be teaching with Audrey Jing. She is super duper awesome. And Audrey has been doing math competitions since the first grade when she took her first math kangaroo contest. She has also qualified for the American Invitational Mathematics Examination multiple times and attended the Math Prize for Girls competition, as well as several other math competitions. So she's very active on that scene over there. In her free time, she likes to read, ice skate, and listen to music. So we are very happy to be doing this live style with Audrey, and let's give her a very warm welcome.
Thank you so much, Sam. I'm also excited to introduce my co-host, Sam. Sam has been participating in math competitions since third grade, and she's placed in the top 5 at the Georgia State Math Counts and qualified for Amy twice, which is a huge accomplishment. She volunteers for the Math and AI for Girls competition, which is super cool. And she's an officer for her school's math team. And in her free time, she loves debate, reading books, and listening to classic rock. I'm really excited to be showing this to you guys today with Sam, and we hope you enjoy the lifestyle.
Absolutely. Okay. With that, for those of you guys who have never been in a live class before, we have a system called Chat Relay that Professor Loh introduced beforehand. And I think a lot of you guys have already discovered this. So basically, if you go to your chat and you type in Chat Relay and send messages, your messages actually pop up on our screen. So we'll be able to see what you guys are saying. So definitely interact with Chat Relay, send messages through that. And we would love to hear what you guys have to say throughout chat.
Yeah. And with that, let's begin with our first question. So today we're going to be covering only the odd numbered questions in Math League. And our first question is number 1 on the sprint round. So the question asks us, lollipops cost 5 cents each and pieces of licorice cost 8 cents each. Anna spends 54 cents to buy 9 pieces of candy. So how many lollipops did Anna buy? So first, I think we should turn the question statement into math that we can work with. So we want to know how many lollipops Anna bought. So maybe we can let this number be L. What do you think, Sam?
Yeah, I think that's a good designation. We'll let number of lollipops be L. And then can we say something about how many licorice pieces there are if there are L lollipops?
So we have that there's 8-cent pieces of licorice and lollipops cost 5 cents each. And so we also know that there's 9 pieces of candy bought in total. So if we know the number of lollipops, maybe we can represent the number of licorice pieces in terms of L, which is the number of lollipops.
Yeah, and I think Stephanie and Ramya both said that the number of licorice pieces is going to be 9 minus L, and that is absolutely right. So now that we have some kind of expressions for our pieces of lollipops and licorice, let's see if we can multiply by their cost to get the total. So we know that a lollipop costs 5 cents each, so we can say that 5L, or 5 times L, plus what's the total cost of the licorice, Audrey?
If we have 9 minus L pieces of licorice and each piece of licorice costs 8 cents each, maybe that would just be 8 times the number of costs per piece. So 8 times 9 minus L.
And that sum is going to be 54. Okay, awesome. And so now we just have to solve this equation. So we have 5L, nothing very fancy going on there. And then we've got to expand the 8 times 9 minus L. So that's going to be 8 times 9, which is 72, and then times 8 times negative, or plus 8 times negative L. So that's minus 8L, and that's going to be 54. And so how can we solve this equation?
So now that we have 5L plus 72 minus 8L is 54, we have terms with an L in it and terms with no L. So we can combine like terms. So first we take the 5L over here and the 8L minus 8L over here, and we can combine that to get negative 3L. And then we see that we have a 72 on our left side and a 54 on the right side. So we can subtract 72 from both sides to get that negative 3L is equal to 54 minus 72, which is going to be negative 18. What should we do now, Sam?
And then we can just solve for L by dividing both sides by 3. And so then we have that L is equal to 6. So that means that there are 6 lollipops. Awesome. And I think a lot of people said this in chat already super duper quickly, which is really awesome. Thank you guys for participating and sharing your answers with us. And if anyone ever has a solution to a question, you guys are also welcome to put that in chat. Any ideas as well, you're welcome to put in chat. And me and Audrey will do our best to incorporate them in the problem solving. Okay.
Yes, we will.
Awesome.
And yeah, our answer is 6. So great job, everybody who participated and found this answer super duper quickly. And now we're going to move on to our next question. So in this question, this is sprint number 3. We have a rectangle ABCD with side lengths AB equals 4 and BC equals 1. And points E and F lie on sides BC and CD, such that BE is equal to DF is equal to 3. And we want to find the area of quadrilateral AECF. So Sam, how should we start with approaching this question?
Well, I feel like AECF is kind of a wonky figure, and I don't know any area formulas for that. But I do know the area formula for a rectangle, and if I subtract 8 triangles ABE and ADF from that rectangle, I get AECF. So I think that might be a better method. So we can maybe try to find those areas.
Yeah, I think that's a great idea. So AECF is a really weird shape to calculate. So Sam's suggesting that we consider a nicer area, which is the area of ABCD, so this entire rectangle, which we know how to calculate, and then subtract off this triangle and this triangle. So basically, we want to find the area of ABCD minus the area of triangle ABE minus the area of triangle ADF. How do we go about finding these areas?
Well, I feel like we can find the area of ABCD pretty easily because we're already given that the length is 10 and the width is 4. So the area of rectangle ABCD is going to be 40. Now we just have to find the areas of the triangles.
Yeah, and now we can use the area of a triangle formula, which is that the area of any triangle is 1/2 times base times height. And the super convenient thing is that we have triangles ABE and ADF, and they both happen to be right triangles. And their heights and bases are actually shown in the diagram. So Sam has given us the area for ABCD, and the area of ABE is going to be 1/2 times the base of 3 times height of 4. And then triangle ADF has area 1/2 times base 10 times height 3. Now we just need to calculate these values.
Yep. So 4 times 10 is 40, and then 1/2 of 3 times 4 is 6, and then 1/2 of 3 times 10 is 15. So we have 40 minus 6 minus 15, and that is going to be 40 minus 21, which is 19. And that's our answer.
Yay, our answer is 19. Again,
Awesome.
I see so many quick answers in the chat. So you guys are doing a great job. And yeah, thank you guys for being so active participants.
Okay, next question. What is the length of the longest possible line segment that can be drawn on a 3x4 rectangular piece of paper? Okay, let's get a piece of paper on our screen.
So this is our 3x4 rectangular piece of paper. I'm going to let mine have height 3 and width 4. And now we just have to think about what is the longest line that could be drawn on here. If we have one that's like straight up like a vertical line, that's going to give us a length of 3. And if we have one that's horizontal, it'll give us a length of 4. But if we tilt our line a little bit, it seems like it gets even longer from the length of 4, which is currently our longest one. This seems even longer than that. And if we tilt it even further and had the line have vertices of 2 diagonal points in the rectangle, this seems like it could be our longest line. What do you think, Sam?
Yeah, I agree. And I've drawn a couple of examples of us progressively tilting the line. And as we tilt the line even more and more so that we get closer and closer to the corners, we see that our length of the line is actually getting longer. So that maximum length is going to be when we connect 2 opposite corners of our rectangle. So if we do that, we've got a right triangle now with side lengths 3 and 4. And if we have a right triangle, I'm already seeing a lot of people in chat saying that we can use the Pythagorean theorem. So let's go ahead and do that. So to find the length of that diagonal, we're going to do 3 squared plus 4 squared is equal to the diagonal squared. So what is the value of the diagonal, Audrey?
So I'm seeing so many great answers in chat of how we can use the Pythagorean theorem, which gives us that if we have a right triangle with legs A and B and hypotenuse C, we have A squared plus C squared equals A squared plus B squared equals C squared. So here our legs are of length 3 and 4 because this is our right angle. And so if we square 3 and 4 and add them together, we are going to get 25. And now we know that the hypotenuse squared must be 25. And the length can't be negative, which means that the length must be 5. So we have that the longest possible line segment that can be drawn here is going to be 5.
Awesome. I totally agree. Okay, let's check our answer, and we're right.
Yay.
Perfect.
Okay, our next question is sprint round number 7, and it asks us for this really scary looking product. We have 3 times 6 over 4 times 5 times 4 times 7 over 5 times 6 times the same pattern over and over, which is n times n plus 3 in the numerator and n plus 1 times n plus 2 in the denominator. And this goes all the way up to n equals 99. And we want to take this huge product and combine it into one common fraction. Wow, how do we start this?
I really feel like something has got to cancel because there's no way they would make us multiply all these ginormous numbers out.
Yeah, I agree. And we can take a look at these fractions that they provided us here on the left. They gave us 3 fractions to just see and write out. And so it's really nice because you can see that things already start canceling.
For
We
sure.
have 3 times 6 over 4 times 5. And the next fraction has 4 times 7 over 5 times 6. And it already looks like the 4 is going to cancel out here. And in the next pair, we have 4 times 7 over 5 times 6 and 5 times 8 over 5 times 6. And it looks like in that
the
case,
denominator of that last fraction should actually be over 6 times 7.
yeah, I agree. It seems the
Okay,
pattern was
perfect.
skipped a little on that one. But yeah,
Go
so the
ahead and guess
5s
that.
also cancel out in the next pair. Is there anything else we can cancel out?
I think that's it. Let's see. Yeah, I'm a little behind you, Audrey. You were super quick for me.
Oh, sorry. Don't want to lose anybody here. But we see the 4s cancel out and the 5s cancel out.
Yeah.
And I think a nice way to think about this is that the numbers are like n and n plus 1, n plus 2, n plus 3. And when you increase n by 1, you're going to see so many repeat values. And I think another pair that might be able to be canceled out is in the first 2 fractions over here, it seems like there's a 6 in the numerator and a 6 in the denominator, which is a really interesting pattern. We don't really get to confirm it. Oh, I guess we do actually, because the 7s also cancel out here. But now the question is, why does this work so well? Where do all these numbers go? And is it going to continue for the next fractions?
Well, I think it will, because if we look at what the general form of the fraction is, we're told that the fractions are made using the formula n times n plus 3 over n plus 1 times n plus 2. And every time we increment n by 1, our numbers are repeating. Like, for example, when we had n equals 3, n plus 3 is 6. But when n is equal to 6, we also have a 6 in the numerator as well. So these numbers definitely show up a lot. And that means that there is potential for this pattern of cancellation to continue even later on in the product. So let's see if maybe we can find a way to figure out how far it takes to cancel.
Yeah, I really like how you mentioned that it's all based on n, which is why it's going to cancel out even past the first few fractions. And I think a nice way to view it is like, if we just look at any set of fractions that are like consecutive, we see that if we start with any number n, we have this, and then we increment all of these things that are multiplying by 1, and we get here. And the nice thing is that we notice that the upper right and the second one's lower right, they're going to cancel out right here where we have like the 6s going away. And we can see why, because here it's like the n plus 3 and the n plus 3 are always going to be there because the n plus 2 gets incremented by 1. And similarly, the n plus 1s are going to go away as well because the n gets incremented by 1 and it goes up on the next fraction. And this pattern continues with these all going away. So for every fraction, the diagonal where it's like the upper left and the bottom right is canceled out by the previous fraction, and the bottom left and the upper right gets canceled out by the next fraction. And so it looks to me like all of these complicated numbers in the fractions mostly go away. What do you think, Sam?
Yeah, I think so too. The only thing that I'm seeing remaining is the first like part of the fraction, that 3/5. It doesn't seem like that's getting canceled out anytime soon. So I think that's going to be a part of our answer. And Audrey, what do you think is at the end of our answer? Like, is there anything we have to multiply by?
Hmm. I think the 3/5 is remaining because we have this like one diagonal that is canceled out by a number before, but because the first
Mhm.
fraction has nothing before to cancel it out, it needs to stay. But there's also a diagonal that's canceled out by the fraction after. But in this last fraction, there's no fraction after to cancel out this diagonal. The 100, the 102/100 diagonal isn't canceled out by anything after in the way that all the other fractions are. So I believe that the parts that are remaining in our product are going to be 3/5 times this 102/100 part. What do
Yeah,
you think?
I agree. I think that totally makes sense. And yeah, I would say that's how we're going to get to our answer. So let's go ahead and expand this product. We can
Yeah,
do a
so
little cancellation with the second fraction, I think.
mhm.
So we can
So we
cancel
get
factor
3
of
over
2.
5 times 51/50. And then it doesn't look like there's anything else to cancel out. So we can combine this to get 153 over 250.
All right, let's check our answer. And that
Yay.
is correct. Awesome. Great job, you guys.
Yeah. Okay. And now our next question is number 9. So we have a fair coin that is flipped 4 times, and we want to find the probability that it lands on heads more times than it lands on tails, and express our answer as a common fraction.
Okay. So I feel like there is like quite a few possibilities, but they're countable,
Mhm.
but that takes time. And I feel like that I don't know. I don't really want to count all those possibilities. So maybe we can think kind of smartly about this and see when we're going to get more heads than tails and how often that occurs.
Yeah, I agree. I think since there's only a coin being flipped 4 times, like Sam said, we could just write all the cases out, but that's a lot of work. And it's a sprint round, so we want to be faster. So maybe we could think about what cases we have. If we want, I'm going to express H for a head and T for a tail. So for example, one like flip sequence could be like head, tail, tail, tail. And that means you flip the head and then 3 tails afterwards. And so this is not a successful case for us because the coin did not land on heads more times than it landed on tails. And because we are only flipping the coin 4 times, I think we can break the cases that we're considering up into not many cases that we can count. Like, for example, one case could be that we have 4 heads, and that means it lands on heads more times than tails because it doesn't land on tails at all. So this could be one case, 4 heads, or we could also have 3 heads and 1 tail because here 3 heads is still more than 1 tail. But then the next case would be 2 heads and 2 tails, and that doesn't work because we don't land on heads more times than tails anymore. And if we continue down and continue decreasing number of heads, we see that these are the only 2 cases that are going to work. So now we just have to calculate how many ways there are to have these flips.
Yeah, and I think we can actually do a little bit of complementary counting here. So the cases that work are 4 heads and 3 heads and 1 tail. And the cases that don't work are 2 heads, 2 tails, 1 head, 3 tails, and then or I think I wrote this backwards on my screen, 0 heads and 4 tails. Sorry about that. And actually, it's really interesting because the probability of getting 4 heads and 0 tails is the same as the probability of getting 0 heads and 4 tails. And similarly, the probability of getting 3 heads and 1 tail is the same as the probability of getting 1 tail and 3 heads. So what we can do is we can subtract the only probability that we haven't matched yet, the probability of getting 2 heads and 2 tails, and then take what's left and divide it by 2, because the probability is equal for heads winning over tails winning. So let's calculate the probability of getting 2 heads and 2 tails. Now that's just going to be 1/2 times 1/2 for the heads, and then another 1/2 times 1/2 for the tails. Well, that's really convenient. That's just 1/2 to the power of 4. And so that's going to be 1/16. So if we take the complement of that, that is 1 minus 1/16, and that gives us 15/16. Now, Audrey, how can we finish this off?
I first of all want to mention that I really love your method. Like this idea of pairing up these cases that work and don't work is really nice because here we have these like 4 cases where we have either 4 heads, 3 heads, 2 heads, 1 head, or 0 heads, and that determines how many tails there are going to be. And Sam is noticing that the probability of having 4 heads and 0 tails, or 3 heads and 1 tail, is the same as 1 head and 3 tails, or 0 heads and 4 tails, respectively. And so what we can do is realize that the cases we want, which are 4 heads and 3 heads, 1 tail, they sum up to the same thing as the cases of 1 tail, 3 head, and just 4 tails total. I think I might have flipped that by accident, but we'll just change it really quick. And so what this means is that out of our total probability of 1, there's really only 1 case that we haven't accounted for in one of these 2 cases, which is the 2 heads and 2 tails, because in that case, they land on heads and tails an equal number of times. And Sam had the really great realization of having each head and tail be a 1/2 chance of being flipped. And so this gives us a 1/2 to the power of 4 chance total for these heads and tails. But we also do need to consider that this could happen in any order. For example, we could have like head, tail, or like tail, tail, head, head. And these are all different flip sequences, but they all fall under this wide umbrella of having the same numbers of heads and tails. And so since we have 4 spots and we want to have 2 heads and 2 tails, we can do a binomial coefficient calculation and choose 2 of the 4 spots to be heads. So that's going to give us 1/2 to the power of 4 times 4 choose 2, which will give us 1/16 times 6. So that means the probability of getting the same number of heads and tails is going to be 6/16.
Yep. Thanks, Audrey, for correcting me on that. I just realized when you were explaining what I did wrong. I appreciate that. So the complement is 10/16. And we talked about before how the probability of having more heads is the same as having more tails. So now all we have to do is divide this 10/16 by 2, and then we get our final answer of 5/16, which I'm seeing a lot in chat relay. So thank you guys again for giving us some answers. And let's check out if we're right.
And
Okay,
yeah,
we
that is
are.
our answer.
Awesome. Really great work, you guys. You guys are doing awesome.
Okay, and now for number 11 on Sprint Round, we're given the 8-digit number 1687198 and it's divisible by 24 for some digit A. And they want to figure out what A is. How do we even begin tackling this? Do we know anything about divisibility by 24?
Well, 24 has some factors. It has the factors of 3 and 8 and 4 and 6. Maybe we can do something with that.
Yeah, so like Sam mentioned, 24 is divisible by many things, which is really helpful in this case. It has factors of 2, 3, 4, 8, and many more, but these are the ones that I know divisibility rules for. So I'm going to focus on these. So first, we think about the divisibility rule for 2. And I'm seeing a lot of answers in the chat, but being divisible by 2 means that it's even, so the last digit must be even. But unfortunately, it doesn't help us a lot because the last digit is already 4, which is even. So divisibility by 2 is not going to be helpful to us here. Next, for divisibility by 3, does anybody know what the divisibility by 3 trick is?
Yeah, I think Albert says that it's added. I think Albert put it in first, but so many of you guys are also doing it. Yeah, the sum of the digits is going to be divisible by 3. So let's go ahead and check that sum. If we add up all of our digits, we have 1 plus 6 plus 8 plus 7 plus 1 plus 9 plus 8 plus 4. And so adding that up, we have to be very careful here not to mess up. We got 1 plus 6 is 7, plus 8 is 15, plus 7 is 22, plus 1 is 23, plus 9 is 32, plus A is 32 plus A, and then plus another 4 is 36 plus A. Audrey, did I do that right?
I think so, but if we made any mistakes, feel free to point out in chat because we are solving these for the first time as well. So we'd love to see if we make any errors.
Okay, awesome. Derek says it's 36. Okay, perfect.
Yay. Okay, so now we have the sum is 36 plus A, of course, because we didn't factor A in because we don't know what A is yet. And because this huge number is divisible by 24, it must also be divisible by 3, which means because of the divisibility trick that Albert gave us, the sum of its digits must be divisible by 3 as well. So we have that 3 must divide 36 plus a. And the really cool thing is that 3 already divides 36. So if we want this total sum to be divisible by 3, a must also be a multiple of 3. So the divisibility trick by 3 gives us that a is a multiple of 3, but that's not enough to know exactly what a is. So what should we do next?
Yeah, so let's continue looking at some of our other factors. We can test for divisibility by 4. Does anyone know the divisibility trick for 4? Yeah, so a couple people are saying that the last 2 digits have to be divisible by 4. Okay, so we're fortunate because we know that the last digit is 4. So let's check out some possibilities when our last 2 digits are 4. Well, I guess we can try a lot of different possibilities. For example, when a is equal to 0, 0, 4 is divisible by 4. If we try 1, 4, that's not divisible by 4. But if we try 2, 4, then that is also divisible by 4. And I'm starting to see some people saying that that means a also has to be divisible by 2 in order for a4 to be divisible by 4. So for example, 0, 4, 24, 44, and so on, all of these work. So we also know that 2 divides a. Okay, now what? Is that enough to figure out an answer?
So now we have that 3 divides a and 2 divides a. And so we can put those two together to find out that 6 divides a. And this seems really great. There's not that many single digits that are divisible by that are divisible by 6. But unfortunately, there are 2. So 6 divides 0, but 6 also divides 6. So now our question is the a that we're looking for equal to 0, or is it 6? Maybe we can use the last divisibility trick that we haven't used yet from our list over here.
Now we're going to look at 8. So what is the divisibility rule for 8?
I see Bernie said it. Divide the first 3 digits by 8. In this case, it would be, I guess it depends on which way you're looking, but divide the last 3 digits by 8. And if the whole number is divisible by 8, the last 3 should be as well. Which means that here we want the number 9a4 to be divisible by 8. And we only have 2 cases left.
Oh, sorry. I was going to say if you wanted to split up and I could do 904 and you could do 964 and we could see which one is divisible by 8.
Oh, that sounds like a great idea.
Okay,
which one do you want to do?
I can do 904.
Okay, I'll do 964.
Okay, perfect. Hopefully I don't mess up my division. Okay, I think my number is divisible by 8. Let's see if yours is.
That's really good because I don't think mine is.
Okay, that's good. Alrighty,
Okay.
so it seems like a is going to be 0 then.
Yay. Let's check if that is the correct answer.
And we're right.
It is.
Awesome job. We love how much chat is blowing up. This is really great that you guys are super interactive.
And it was really great that you guys helped us with like checking our sums and giving us divisibility rules. So keep it up, you guys.
For sure. Okay, let's do problem number 13. Oh, lots of letters in here. Okay, we want to find the minimum possible value of a squared plus b squared plus c squared plus 2a plus 4b plus 6c plus 8. Okay, this seems a little bit difficult, but I think we can do it.
Yeah, I agree. So this looks really unapproachable, but I think if we think about the parts of this, it might get a little bit easier. So maybe like, first, if we think about the first part, which is like these squares, a sum of squares, what do we know about squares? What is like the smallest value for a square? I see Isaac also mentioned it's a quadratic. Yeah, hold that thought. I think this can be written as a quadratic, maybe. That is really smart. Should we try that out?
I think that's a pretty creative idea. Let's give it a shot.
Okay, so I think what Isaac is noticing is that we have some square terms, some linear terms, and this constant term. So how great would it be if all of these just happen to work out to end up creating some quadratics for us? So what we
Super
could do,
great.
we can split it up by letters. So for the a's, we have a squared plus 2a. And then we also have b squared plus 4b and c squared plus 6c. Now we're just missing some constant terms. And I think we would want to complete the square in order to make these into some nice quadratics for us to work with. So what constant terms do I need to add to each of these quadratics to do that?
Well, we would have to add the coefficient of the second term divided by 2, and then the square of that. So for example, for a squared plus 2a, that kind of looks like a plus 1 whole squared, except we're missing that constant term of 1. So we would have to add a 1 for that. And then for b squared plus 4b, we would have to add a constant term of 4. And then for c squared plus 6c, we'd have to add a constant term of 9. So let's go ahead and do that.
Yeah. And so now we have that these tricky expressions that we couldn't figure out, once you add these convenient constant terms, they actually turn into some really nice squares. And so if we add up all of these three equations, we're going to get that a squared plus b squared plus c squared plus 2a plus 4b plus 6c plus 1 plus 4 plus 9, which is 14. That's going to equal all of these really nice squares. But the problem is that we don't have a plus 14 term. So what should we do?
Well, I guess we'd have to subtract that 14 so that our equation remains balanced. So if we go ahead and subtract that constant, so that way we don't actually change our equation, we get negative 14 plus 8, and that's going to give us a negative 6 term. So we get a plus 1 squared plus b plus 2 squared plus c plus 3 squared minus 6.
Wow, that's a really much nicer expression to have to work with. And I think this is going back to our original question of what do we know about things when they get squared? What is the smallest value that a square can take? Because now that we have 3 squares plus a constant, knowing that would give us the answer.
Derek and Sunscreen both said 0. Okay, awesome. So we're going to let each of these values be 0. And that minimum value is attained when, for example, a is -1, b is -2, and c is -3. And if we get that, the sum of all those squared terms is 0, and then we've just got a -6 at the end. So that minimum value is just -6. Wow, that was so nice. That was such a clean solution. Thank you to Isaac, I think, who initially suggested the idea. And if anyone else solved it like that, that was really creative. So great job.
Yeah. And our answer is -6. Great job, you guys. And thank you for all the solutions and ideas that you provided.
Great. Next question. Number 15. All right.
So we have an...
Oh, sorry. Go ahead, Audrey.
Okay. We have an equiangular hexagon with 4 sides of length 2 and area 60 root 3. And we want to know what its perimeter is. So first of all, equiangular means that this hexagon has 6 angles and all of them need to be equal. But unfortunately, this does not mean that the hexagon has all 6 side lengths are equal. So our equiangular hexagon could look something like this. It has some really long sides and then 3 really short sides. Oh, that was a terrible last side. But still, it's going to have 6 angles of 60 degrees. And so, oh, here we actually have 4 sides of length too. My bad, I misread that. Let me change my diagram a little bit.
I think I might have drawn it backwards. I don't know if 2 is the longest or the shortest, so I just made it the longest. So this diagram is not to scale.
And yes. Okay. And we're given that its area is 60 root 3, and we want to find its perimeter. Wow. How do we approach this?
I mean, I know how to find the area of a normal hexagon, but this hexagon has some sides of different lengths. So I don't think we can do that here. But maybe we have the area, so I feel like we should definitely try splitting this up. And maybe we can draw, I feel like maybe we can draw a rectangle outside of this hexagon and see where we go with that.
I think so. I also think that the equiangular part is really convenient because normally when I calculate the area of a regular hexagon, I use the equal angles a lot. And I think here maybe we can split our hexagon up like this along this side. And so we know that all of the angles need to be 120. I might have misspoken earlier and said 60, but no. If it's an equiangular hexagon, all the angles are 120. So if we split it up here and it's symmetrical, it seems like both of these angles should be 60. And then because we have these two angles of 60, maybe we can extend these two side lengths out and create like what should be an equilateral triangle on both sides, if I'm not mistaken.
Oh yeah, I like that a lot.
Hopefully that works. So because we have two angles of 60, our last angle must also be 60. And I think if we let our missing side length be x, I believe the top part is also an equilateral triangle. What do you
Yes,
think,
I
Sam?
think so as well. Because that internal angle of this side over here is actually going to be 120. And so when we take the supplement of that, that's going to be 60. And so the other side is also 60 by the same reasoning. So we get a triangle with degrees 60, 60, 60, which is an equilateral triangle.
Okay, that's wonderful. So now I think we can calculate the area in terms of x because we have that we've split this weird hexagon into these two shapes that are basically one big equilateral triangle of side length 2 plus x, and then we cut off this little equilateral triangle on top of side x. And so if we use the area of an equilateral triangle formula, which you can also derive from 30, 60, 90 triangles that you can split it up into, but the area is going to be √3/4 times the side length squared. And so here we can actually calculate the area of one of these like trapezoids because it will be √3/4 times the big side length, which is x plus 2 squared, and then subtract off the side length of the little triangle, which is √3/4 times x squared. And now we just need to evaluate that. And don't forget to multiply by 2 because this is only going to be half of our hexagon.
Yep. Good catch, Audrey. Okay, awesome. I'm actually going to write this on a different screen, so that way we have space to evaluate.
That's smart. I think I'm running out of space too.
Okay, I went ahead and grouped everything. So the constants are taken out of the expression, and then we've just got x squared plus 2, or x plus 2 whole squared minus x squared, and that's going to be equal to 60√3, I believe. Okay, awesome. So now we're just going to go ahead and simplify. So we have 2√3/4 times x squared plus 4x plus 4 minus x squared is equal to 60√3. So 2√3/4 times 4x plus 4 is equal to 60√4, or √3, sorry about that. And we can do a little cancellation now. So the 4 in the denominator actually cancels out with the 4 term, or with the factor of 4 in the expression itself. So if we go ahead and cancel that, we get 2√3 times x plus 1 is equal to 60√3. And then we can divide both sides by 2√3 to get that x plus 1 is equal to 30. So that means x is equal to 29. And so that means my original diagram was very wrong. That side length of 2 should have been the smaller one. I drew it as a longer one. Yeah. Awesome. Audrey, are you getting the same thing?
Yeah, I got the same thing as you.
Okay,
X is equal to
perfect.
29.
Great. Let's check our answer. Oh,
Oh
no, we are not
no.
right.
What
Okay,
happened?
oh my gosh, wait, that's not our answer because it asked for the perimeter.
Oh, good catch. Oh
Okay,
my
so let's
gosh.
find the perimeter. So we got 4 side lengths of 2. So 4 times 2 plus 2 side lengths of 29. And so that's 8 plus 58, which is 66. And that is our answer.
hmm
Okay, awesome. So yeah, always go back and read the question. That's
Yeah.
very important.
Okay. Anyway, our next question is 17, and we want to find the radius of a sphere inscribed in a right circular cone with height 6 and diameter 5. Wow. So I'm going to attempt to draw a right circular cone with these dimensions, but it might go a little badly.
Yeah, 3 is
So
very hard to draw, but
Yeah.
Respect to people who can.
hmm Okay, I think it's actually not that bad.
Yeah,
So
that's
if
a
our
really nice
diameter is
drawing.
5, then our radius will be 5/2, and our height is going to be 6. Okay, and now, oh, the hard part. We need to inscribe a sphere in here. Oh God. Okay, that is definitely not a circle, but hopefully it's close enough. Okay.
I'm gonna draw my sphere in yellow.
Oh, a color change would be really nice, just so it's a little easier to see.
Okay,
I would
mine
do
looks
that.
like an egg or like an oval or something. We would recommend that you guys also draw your own diagram on paper because
Yeah.
ours might be slightly inaccurate. Okay, and
Mhm.
we want to find the radius of the sphere. Okay. I mean, when I see 3D stuff, I like to take sections of it to
Mhm.
see in 2D. And these are called cross sections. So maybe we could take a cross section here, Audrey. What do you think?
Yeah, I agree. I think it
Okay,
would be
awesome.
really difficult to work with this if it was in 3D, so a cross section is a really good idea.
Okay, perfect. Let's go ahead and do that then. Okay. So we've got a triangle on the outside, because that's like kind of what our cone is made up with. When we consider a cross section, we kind of like are cutting it like straight down the middle. And so when we cut it, we don't really worry about the circular base. We're more concerned about the fact that the figure that we're cutting has a triangle on the outside, and then like it's got a little slice of sphere in the middle. So if we go ahead and draw that, we get something that looks like this, or something that looks like what's on Audrey's screen, because she's much faster than me at drawing.
But yeah, this is a cross section I have, and I think it's really convenient because the points where the sphere is touching this right circular cone are reflected into these like points of tangency between the circle that is a cross section of the sphere and the triangle that is a cross section of the cone. And so we still have that. If we want to find the radius, it's still going to be this length that we can work with kind of because it is going to be tangent to both of these.
Yeah. Okay, awesome. And I'm seeing a couple people drop a formula in the chat that I think is probably very helpful for this question. It's the fact that the area of the triangle is equal to the radius times the semi-perimeter. I think we should go ahead and use that. What do you think, Audrey?
I agree. And I think it's
Okay.
nice because this formula is really intuitive to me. If you look at this diagram, the semi-perimeter is just like one half of the perimeter, right? So if the side lengths were like A, B, and C, the semi-perimeter would be one half of A plus B plus C. And when we multiply that by the radius, it's giving us these like one half AR plus one half BR plus one half CR. And each one of these things that we're summing up is the area of one of the triangles. Like if A is this side length, one half A times R is going to be the area of this triangle. Let me just shade it in really quickly and then undo it. But this is because R is the height and A is the base. And so obviously when you add these three things up in our sum, we're going to get the area of the entire triangle that has the circle inside of it. And yeah, I think we can proceed to use this formula. It'll be very
Yeah,
helpful.
that was a really good explanation. Thanks for diving into that, Audrey.
Thank you. And so now we can use this formula of the area being equal to the radius times semi-perimeter. And this is because we actually know we can find the area and the semi-perimeter pretty easily from what we have. So how will we go about that?
Okay, I see a couple of people saying Heron's formula, and then I see a couple of people saying don't use Pythagorean theorem. So I don't know, like I'm kind of torn here because I can't see how to use Pythagorean theorem, but I also like I don't know. I mean, I get Heron's formula, but maybe I don't know. What do you think? Like there's two methods here. It's up to you. Like how should we go about this?
I see the point of view of all the Pythagorean theorem haters out there, but honestly, I think we should just go ahead and do it. We are
Okay, let's
given,
bash it out. I think
yeah,
we
we
could
do
do
have the
this.
height and the base.
I think it's
So,
actually it shouldn't be too bad, I feel like.
mhm,
We'll see.
yeah, the area at least is easy because we have the height
Yeah.
and the base. So it's just gonna be 5/2 times 6. And now we get to the Pythagorean part. So we can let the side length of this be h. And if we look at just like half of this diagram, oh wow, I'm really running out of space. But I'm going to go on to a new page, I think.
Okay, awesome. I think I have a little bit left, so I'm going to finish up here, and then maybe I'll switch in a second.
Okay, so we have the area, which is going to be 5 over 2 times 6, and we want to find the semi-perimeter. And to find the semi-perimeter, we need to know what h is. And h is the hypotenuse of this right triangle that we have the leg dimensions of. So h is squared is going to be 5 over 2 squared plus 6 squared, which ends up being 25 over 4 plus 36. And
I
I
think it
think that
actually
is,
might be helpful to maybe rewrite 6 as 12 over 2, because I see a really nice triangle once we do that.
ooh, wait, I really like that actually. That is very smart. Let's see what happens if we do that. Okay.
Okay, so we have a right triangle that has a short leg of 5 over 2, and then rewriting the 6 using the half, like just converting it, we get 12 over 2. So we're kind of going backwards in simplification, but it's okay. And so now we see something that's similar to a 5, 12, 13 right triangle, which is super duper common, except it's all the sides are multiplied by a factor of 1/2. And so if our hypotenuse should be 13, because we've got a factor of 1/2, our hypotenuse in this new triangle is 13 over 2. And I think that's much faster than the squaring of the things and maybe potentially making a mistake.
Yeah,
So
I
this is
agree.
nice.
And this way, all the people who didn't want to do Pythagorean theorem, you don't really have to do it now. If you can see the 5, 12, 13 triangle, which by the way is a really good triangle to sort of recognize when you do math
For sure.
competitions. If you can see that and you notice that we have a 5 over 2 and a 12 over 2, like Sam did, this makes it really easy to realize that the hypotenuse has to be 13 over 2.
Yeah. Awesome. So now let's go ahead and find that semi-perimeter. We just add up all the sides and divide by 2. So 13 over 2 plus 13 over 2 plus 5 is going to be 18. Addition is hard. And then 18 over 2 is 9. Awesome. So we have 15 is equal to 9 times the radius. So Audrey, what is the radius?
Yay, we're in the final stretch here. So the area is 5 over 2 times 6, and the 2 and the 6 cancel out each other to get a 3 on top. So we get 15 is equal to 9r. And then dividing both sides by 9 gives us that the radius is 15 over 9. And finally, a little more simplification, we can divide both top and bottom by 3 to get that the radius is 5 over 3.
Awesome. Okay, this was really great. This was a question with a lot of different like tricks involved. So it's kind of it's important to understand them, but hopefully like any tricks that we use, you guys understand why they work because that's something we really want you guys to be able to get away from this. So let's go ahead and check our answers. And we're right. Awesome. Okay, next question. All right, question number 19. So we've got an 8 by 8 grid of unit squares, and we're asked to find the expected number of unit squares that share an edge with a randomly chosen unit square. Oh, this is interesting. Expected value questions are pretty cool. Okay, let's take a look. I don't really want to draw an 8 by 8 grid, so I think I'm going to draw a smaller grid, and maybe we can work with a smaller grid and work from there. What do you think?
I agree with that.
Okay,
Yeah, I
perfect.
don't really want to draw that either.
Great. I'm going to change colors as well because I'm getting kind of bored of white.
So I drew
I'm
a
gonna
3
do
by 3 grid.
Okay, perfect. I'm gonna do 4 by 4 just so that we can get a
Uh-huh.
couple of examples on the screen.
And it looks to me like this would sort of depend on where your randomly chosen unit square is. If we pick a unit square that ends up being one of these in like the border, it looks like the expected number of unit squares to share an edge will be smaller because you lose the potential to have a square like here or here, and you only have these two instead. Whereas if you pick something in the middle, let me change colors just to make it a little more obvious. If we pick something in the middle, the expected number of squares to share an edge with you is pretty big. You can have one in all 4 directions. And it's a similar difference if you pick one that's like sort of on the border, but sort of not. Like one over here. What do you think, Sam?
Yeah, I think that's maybe why we're asked to find expected value because it changes or the number of edges shared or unit squares that share an edge changes for every unit square. So maybe we have to do a little bit of casework for this question.
Yeah, I think so. And I think your 4x4 square might be a little better than mine because it actually shows that as you increase the dimensions past 3 and 4 and whatever, the number or like the part of the square that's taken up by the yellow and the like green parts is not going to be very big, but the pink part gets bigger because everything that is not on the
Yeah,
border doesn't really go through, doesn't have as many options for having a square that it touches.
I agree. I agree. Okay, so let's take a look at some of these values. So let's say, for example, okay, we're asked to find expected number of unit squares that share an edge with a randomly chosen square. All right, so let's say we share, is it possible to share 0 edges? Is that even a possibility?
Hmm. I don't think so. I think the worst case would be like the yellow square here where it's like in the corner because
Yeah.
that way, like there's only 2 spots I could share an edge with it. But I don't think it's possible to have 0 spots.
Okay, I agree. I agree with that. So let's take a look at how many squares share 4 edges. Like you said, it's the ones in the corner. I don't think the ones like on the sides that aren't in the corners work. And obviously the ones in the centers don't work. So it's just the 4 corners of the square. So we can put four types of squares where only 2 sides are shared.
Yeah. And I think even though our diagram is like only showing like 3x3 or 4x4, we are going to imagine that it is for 8x8. So even in an
Yeah.
8x8, there's still only going to be 3 of these like really corner or like, okay, they're actually just corner. Let's call the yellow ones like corner squares. The green ones are like edge squares maybe. And then the middle ones can be center squares.
Yeah, I like that. I like that labeling. We can do that.
So in an 8x8, there's going to be 4 corners. And then I think there will be, would it be 24 edge squares? Because there might be 6 on each side.
I agree with that. Yeah. So if we take a look at the diagram over here, it's a 4 by 4, and we have 2 edge squares on each side because on each side we're not including the corners. So that means for each side we subtract 2, and then we multiply by 4 because there are 4 sides. So in a 4 by 4 grid, there would be 8 edge squares, and in an 8 by 8 grid, we would have 6 squares on each side that are edges, and then for the 4 edges in total, we would have 24 squares. And then we can find the number of center squares using math, and we can find it using 2 different ways. I think I'm going to go with the way where we just subtract the 2 and 3 squares from the total squares. So doing that, we have 64 total squares minus 4 squares with 2 edges and 24 squares with 3 edges. And when we subtract, we get 36. Does that sound right?
Yeah, that sounds
Okay,
right.
awesome. 36 squares. And
Oh, wait,
now,
actually, no. I think it might be
oh, just
32.
kidding. Oh, 32. Wait, maybe I can't subtract. Let's see. 64 minus 28. Wait, I'm still getting 36. Am I
Oh,
like
wait.
tripping?
Okay, no, I'm sorry.
Okay, I think
I think
Rohan
I
also said
multiplied
it's
the wrong thing for
36.
a total.
Oh, okay. No, you're so good. Okay, so I think it is 36. Okay. Sometimes arithmetic can be tricky, you guys. Always check your work.
Hmm. Yeah, and it would make sense because it'd be like 6 squared because it's like you
Yeah.
have the 6 from each edge that come in and sort of make like a smaller square in the middle.
Oh, right. That's another way of thinking it.
Hmm.
Okay, awesome. So now that we've done our little bit of casework, all we have to do is multiply our numbers and probabilities to get an expected value. So I'm going to go to another slide just so we have some space. And so every square has a probability of 1 over 64 of being chosen. So what we can do is we can actually just multiply by 1 over 64 at the very end and then calculate each of the expected values in between. So for corner squares, we have 2 edges shared, and we have 4 corner squares. So we would do 2 times 4 for the expected value. What about the edge squares, Audrey?
Hmm. So our edge squares, we found that there were 24 edge squares. And so we can go back to our diagram and see what the expected number or the number of possible edges it could share with other squares is. So this would be our edge square, and it could have one on top to the right and one to the bottom, but it can't have one to the left because there's nothing there. So I think all the edge squares could have a total of 3 shared edges.
Yeah, I agree. Awesome. And then we finally have our center squares, and our center squares share an edge with four different squares because they share an edge on every single edge or on every single side. So we would have 4 times our 36 edge squares. So now we just have to multiply this out. So doing that, we get 1 over 64 times 8 plus 72 plus 144. Wow, that's a big number.
And yeah, so we can add the 8 and 72 first because that ends in a 0. So we get 1 over 64 times 80 plus 144. And then we add again, and we get 1 over 64 times 224. And now I think there's a lot of simplification that can be done. 64 should be divisible by 4, which, and also 224 should be as well, kind of a callback to our divisibility by 4 trick. So if we divide both those out, we should get 56, I believe,
Yep, I
over
agree.
16.
Yeah, and then we can cancel out a factor of 8.
Hmm.
So 7.
That would give us
and
7 over 2.
Awesome. So they're both divisible by 32. And 7 over 2 is our final answer. Neat. Okay, let's check that last one really quick. And we're right. Okay, awesome. And we're also very on time because it is precisely 8 o'clock. All right. So I know we didn't get to finish all the sprint round and the target, but hopefully you guys learned a little bit of something with the questions we did do. And thank you so much for joining us for today's live stream. You guys are a really great audience. We really loved having you guys. And you guys gave us a lot of super awesome ideas. So thank you so much again. And yeah, see you all next time. Bye, everyone.
Thank you guys. See you guys next time. Bye.